Welcome to Math 401, Applications of Linear Algebra. I'm Jeffrey Adams, and I will be your professor for this course. I'm trying an experiment this semester. I'm teaching this course in a very new way for me. I'm going to be producing a series of video lectures. Each lecture will be about 1/2 an hour long, and there will be one for each class. I'm going to post these videos online, and I'm going to expect that everyone will view each video before you come to class. In class, we'll review the information in the video, and then have time for a classroom discussion, go over examples, answer questions, do homework problems, and so on. There will be a brief quiz at the beginning of each class on that day's video. If you've watched the video, the quiz will be very easy. Here's the class website. If for some reason you can't remember that, you can just Google me and click I'm feeling lucky. Here's my email address. That's a good way to get a hold of me. My office hours and phone number and so on are also found on the class website, where you'll also find the syllabus, the textbook, the grading policy, homework assignments, all that good stuff that you expect to find when you take a class. We're going to be using an online teaching system called Canvas. That's not quite up and running yet, so stay tuned for that. I hope you'll bear with me. This is a new experience for me. I think it will prove to be a great way to learn. So, let's get started. Linear algebra is the study of systems of linear equations. I'm going to assume that everybody is at least a little bit familiar with these. So let's do an example of a system of two equations and two unknowns. Consider the equations 2x plus 3y is equal to 1 and 4x plus 2y is equal to 6. And of course, the problem is to find x and y, which make both of these equations hold simultaneously. The basic idea, given a system like this, is to look, for example, at the coefficient of x. Here you see a 2, here you see a 4, and what that says is that if I multiply this equation times 2 and subtract the two equations, that will cancel out the x. So let's see how that works. You take this equation and you multiply it times 2 to get 4x plus 6y is equal to 2. And now we subtract the 2, and 4x minus 4x is 0. 2y minus 6y is minus 4y. And 6 minus 2 is equal to 4. And we conclude that y is equal to minus 1. Okay? And now to figure out x, what we do is we go back into one of the earlier equations. It doesn't really matter which one. For example, take this one, and right here, set y is equal to minus 1. And then what you get is 4x minus 2 is equal to 6, which says that 4x is equal to 8, and x is equal to 2. Okay, let's look at another example. Let's take an example now with two variables and three equations. So consider 2x plus y is equal to 4. 3x minus y is equal to 1. And x plus 2y equals 5. So, since there are more equations than unknowns, maybe this system of equations does not have any solutions. So what I'm going to do now here is suggest that you pause the video and work out the system of equations on your own. And when you're done, play the video again and we'll see what the answer is. Okay, go ahead and pause. Okay, welcome back. I'm sure you've all worked out the solution to this equation. Let's see what we get. So one thing we could do is, let's see, we could take this first equation, take this 2, and the coefficient here, which is 1. And so we see that if we multiply this equation by 2 and subtract the first equation and the third equation, we'll cancel out the coefficient of x. So if we multiply this by 2, we get 2x plus 4y is equal to 10. And now we want to subtract this equation and this equation. Which order do we want to subtract them in? Well, let's see, 4 is bigger than 1, so let's take this equation minus the first equation, and the 2x minus 2x is equal to 0, and 4y minus y is equal to 3y, and 10 minus 4 is equal to 6, which says that y is equal to 2. Okay, well, now let's figure out x, say. So let's plug y is equal to 2 in here, and that's going to give us 2x plus 2 is equal to 4, and that says that x is equal to 1, I believe. Good. Okay, so now what have we done? We've solved simultaneously this equation, the first one, and the third one, which we multiplied by 2 and made it equal to the next one, but those are the two equations that we've solved. So, and they only have one solution. X is equal to 1 and y is equal to 2. So in order to see if this equation holds, we just have to plug in x is equal to 1 and y is equal to 2 and see what we get, which is that 3 minus 2 is equal to 1. Well, that's certainly true. So therefore this equation does have two solutions. X is equal to 1 and y is equal to 2. Okay, now let's go back and look at our first example again from a different point of view. So that was 2x plus 3y is equal to 1, and 4x plus 2y equals 6. And we did some formal manipulations with this to solve it, which is to say we looked at the 2 and the 4 and we multiplied this by 2 and turned this equation into 4x plus 6y is equal to 2, and so on. And if you think about it for a minute, it's pretty clear that this x and this y are just coming along for the ride. They're not really doing anything. So it's very convenient to get rid of them. And instead of the left-hand side of this equation, which has got all these x's and y's in it, is to simplify it and just look at the coefficients and write down 2, 3, 4, 2. And you put parentheses around this, and I'm sure you all know this is an example of a 2 by 2 matrix. And similarly, you take this over here and you write them as 1, 6, and that's an example of a vector. And what we're going to do now is have a little digression and talk about some formal operations on matrices and vectors, which are then going to be what we use to simplify solving systems of equations. Okay, so a matrix is just a rectangular array of numbers. So, for example, 2, 1, 3, 4. This is a 2 by 2 matrix. So 2 by 2 means it has 2 rows and 2 columns. And for example, I'll write down a 2 by 3 matrix, for example, would be something like 1, 2, 3, 4, 5, 6. And matrices can come in any size, any m rows by n columns, m rows and n columns. So, for example, if you have any numbers a1 through an, you can put them into a 1 by n matrix. Or you could also put them into a column, a1, which would be an n by 1 matrix. Okay. Now, there are two basic operations on matrices. Well, three, depending how you count. There's addition, multiplication, and also scalar multiplication. So let's just do a couple of quick examples. So addition of matrices, if you have two matrices of the same size, you add them just by adding their components. 2 plus 1 is 3, 1 plus 1 is 2, 3 plus 2 is 5, and 4 plus 3 is 7. If you have two matrices of different sizes, either different number of rows or different number of columns, you cannot add them. And scalar multiplication is very easy. That's a scalar is just a number, and the way you multiply a number by a matrix is you just multiply it into each coordinate. 2 times 1 is 2, 4, 8, 10, 2. Notice that both of these operations excuse me, keep the same size of the matrices. You add two matrices and you get another matrix of the same size, and when you multiply a matrix by a scalar, you get another matrix of the same size. Now, let's look at matrix multiplication. This is slightly trickier, but it's really something you're familiar with. Everybody knows about the dot product. The dot product of two vectors, for example, 1 dot 2. The vector 1, 2 dotted with the vector 3, 4 is the vector 1 times 3 plus 2 times 4, which is to say 11. And I said vector, but of course I meant number. If you take the dot product of two vectors, you get a number. Now, I can write the same dot product where I write the second vector as a column vector, and I still have the same dot product. This is 11. And that's basically our first example of matrix multiplication, and general matrix multiplication is just built out of a bunch of those. So here's an example. To multiply 1, 2, 3, 4 times 1, 2, we're going to do two dot products. So the first dot product is where we look at this first row and then this column matrix, and you take their dot product, which gives 1 times 1 plus 2 times 2, which is to say 5. And for the second one, you take the second row and still look at this column to get 3 times 1 plus 4 times 2, and I believe that that is equal to 11. So the matrix, this matrix product is 5, 11. And now the answer is a new matrix. This 2 by 2 matrix times this 2 by 1 matrix, or vector, gives us a 2 by 1 answer. Okay, so let's talk about matrix multiplication in general. So let's do an example. Let's say we have a 2 by 2 matrix, 1, 1, 2, 3. And let's see how to multiply this by another 2 by 2 matrix, 2, 1, 1, 1. And let's write the answer down here. Now, this first matrix has 2 rows. And the second matrix has 2 columns. So there are 4 dot products that I could take. The first row or the second row dotted with the first column or the second column. So you're going to get 4 numbers in the answer. So the first one, and you put those into a matrix. So the first one is the first row dotted with the first column, which is to say 1 times 2 plus 1 times 1. And then you do the first row dotted with the second column, which is to say 1 times 1 plus 1 times 1. And now you go to the second row dotted with the first column, which gives 2 times 2 plus 3 times 1. Whoops, excuse me. And then finally, the second row times the second column gives 2 times 1 plus 3 times 1. And lo and behold, the answer is 2 plus 1 is 3, and 1 plus 1 is 2, and 4 plus 3 is 7, and 2 plus 3 is 5. Okay, so in this example, I'm going to label the number of columns here as 2, and the number of rows here as 2, and I'm going to label the number of rows here as a green 2. And let's label the number of columns here as a yellow 2. Now, I know that's a lot of 2's, but the significance of this is that these dot products that I did all involved a row, which has 2 entries in it, and a column, which has 2 entries in it. And those 2 numbers have to be the same. On the other hand, this 2, the green 2 and the yellow 2, aren't as important in that regard. And that gives us an idea about how to do this in general. Okay, so let's talk about multiplication of general matrices. So suppose I have a matrix, and I'll draw it as not being square to indicate that the number of rows, which is m, and the number of columns, which is n, are not necessarily equal. And let's multiply this by another matrix, and this other matrix I'm going to make, I'll draw it like this. And this matrix I'd like to have n rows, but the number of columns is possibly something different. Call it r. Yes, that's an r. Okay. Now, I can multiply these two matrices because every time I take a row of this matrix, which has n entries, and a column of this matrix, I can take their dot product. And how many dot products am I going to get this way? Well, I have m different choices of row here and r choices of columns here. So the number I'm going to get is going to be m times r. And you put those into a matrix, and the answer is going to be a matrix of size m by r. Okay? Okay, so before I do an example, I'd just like to write this down. The way I like to think of this is you can multiply an m by n matrix times an n by, n by r matrix. You need to have that this n is equal to this n, and you sort of think of those as canceling, and the answer is an m by r matrix. So let's do an example. Let's take a 2 by 3 matrix, 1, 1, 1, 2, 1, 2, and multiply it by a 3 by 3 matrix, 1, 0, 1, 1, 1, 0, 1, 2, 1. What size am I going to get? Well, this 3 and this 3 are the same, so that's good. And then what I get left is 2 by 3. So the answer should be a 2 by 3 matrix. 2 by 3. And let's see, so the first entry, for example, is the dot product of the first row by the first column, which is 3. And then the first row and the second column is 3. And the first row and the third column is 2. And then the next 3 entries are you take the second row times dot product with the first column is 5. Dot product with the second column is, again, 5. And the dot product with the third column is 4. So that defines matrix multiplication in general. Now, notice that if you have, most of the time we're going to be multiplying matrices of the same size. So if you have an n by n matrix A and another n by n matrix B, you can multiply them and get another n by n matrix C. And you could have done it in the other order. I could have multiplied B times A, and let's call that D, which is another n by n matrix. And probably you all know that the commutative law does not apply for multiplication of square matrices. A times B, A times B is not necessarily equal to B times A in general. It might be, but you can certainly find examples of matrices where these two numbers are not, these two matrices are not equal. Okay, so there's just one last thing to go over, which is vectors. And as I mentioned before, a vector is really just a special case of a matrix. So for example, 3, 2, 1, you can think of that as a 1 by 3 matrix. But more commonly, you'll just think of it as being a vector. And if you want to indicate how many coordinates it has, you might say that it's a 3 vector. And sometimes we'll also write vectors as columns. We'll think of this 3, 2, 1 also as being the same 3 vector. And the way you add vectors is just like adding matrices. You add them component-wise. 2, 3 plus 2 minus 3 is 4, 0. And the way you multiply a matrix times a vector is just a special case of matrix multiplication. 2, 1, 1, 1 times 1, 2 this is going to be another 2 by 1 matrix, or that is to say another 2 vector, and it's equal to 2 times 1 plus 1 times 2 and 1 times 1 plus 1 times 2, which is to say 2 plus 2 is 4, and 2 plus 1 is 3. Excuse me. So usually we're going to be multiplying an n by n matrix and we're going to multiply it by an n vector, and we'll think of it as being a column vector. And when you do that, you get out a new n vector. Just like in this example.